but I never did update it. I just who's it? I said, yeah, no, just use the same one from last year. It'll be fine. I totally forgot I had a new position.
All right, well, swap spots real quick. I'll get everything going. All right, folks. It's 2:30, and Jeff's got a lot to say, so we're gonna get everything started. Welcome back. My name is Drew Kirkman. I'm from Hubbard Radio Cincinnati, and I'm a member of the program committee for the Midwest Broadcast Multimedia Technology Conference. I hope you enjoyed your lunch and had time to visit with our exhibitors. Thanks again to our friends at Nautel for their sponsorship of the lunch. All right. Many individuals new to broadcasting and broadcast engineering have a background in IT, and I am no exception. I spent many years as a systems and network administrator before making the jump to radio. While IT skills are essential for many new innovations in broadcasting, many outlets still broadcast over the air. So today, this afternoon's breakout session will review basic electronics and troubleshooting skills for RF systems. And we're pleased to have a familiar face, Jeff Welton from Nautel, to do that for us. Jeff is Nautel's sales manager for the U.S. Eastern region. He previously spent 16 years as Nautel customer service technician, transmitter site visits, house calls, blah, blah, blah. I'll use your words for that. However, he has been widely recognized for his work, earning the NAB Radio Engineering Achievement Award in 2020. The Association of Public Radio Engineer Achievement Award in 2019, and SBE's Educator of the Year Award in 2017. Jeff, thank you so much for your willingness to present today and for Nautel's support of MBMTC.
Thank you.
Yeah.
That was kind of cool. It's almost like I wrote it myself. Well, the first half, Drew did that. The good sounding half, that was all Drew. The rest, that was on me. So I've got a timer set for 37 minutes. We're going to run it until it buzzes in my hand, like I said earlier, and then I'm going to jump, squeal, and launch it across the room. Whoever catches it will win a door prize. I'll try not to throw it that hard. So the topic is, first question, how many people are originally trained in IT and have learned radio RF kicking and screaming? Next dumb question. You remember this morning, I'm full of dumb questions. Well, don't expect this to be any different. How many people are familiar? I'd rephrase. Is there anybody who's not 100% certain of what Ohm's law is? Couple? So y'all are the ones this is for. Now, the question is, why do we do a session on RF for the IT oriented, or RF, or why do we do this at all? And so I showed this to Chris Merritt earlier and drew an audible gasp. This is the average age of the broadcast engineer taken directly from the SBE salary survey that's published every year. And on the left, you got 2001. In the middle, you got 2011. On the right, you've got 2024. I apologize for the different formatting of the graph. The first two were done by John Perret in a paper he presented at the NAB. The last one was all me. The numbers I added down below. So out of 400 and some odd respondents, 18.1% are 66 and older. If that doesn't scare the pants off you, it should. Because it's awesome that folks are able to work in this industry that long, but at some point, Mother Nature's going to take toll. And we're going to have to be fixing stuff and finding folks to fix stuff. And I said, if we don't find a way to bring more young folks into this industry, and that's where I keep beating Gary and the folks at the SBE over the head, if we can't bring more young folks in, we're going to hit critical mass where there's not enough people to repair stuff. Because coincidentally, transmitters, although they've moved to solid state, and there's no big tubes as much, they're still out there. They tend to still fail at the same annoying rate they always did. The only difference is now you're not off air, you just got a red light. Still needs to be fixed. So the first thing that happens is people tend to get terrified. You got a red light, we're off the air. General managers call in every 30 seconds. How long are we going to be till we're on the air? Well, it's going to be another 5 minutes now because I got to back out what I was doing to answer the phone. Now I got to get my head back in, get back in there, and start all over again. So, this is where I was going to shut the phone off if you don't shut up and stop calling me. bite-sized pieces. Break everything down into bite-sized pieces. Every transmitter on the planet, I don't care whether it's a cell phone, an FM, an AM, a television, an STL, every transmitter, 5 blocks. Okay, you've got the exciter where the signal comes in and gets turned into whatever you want to amplify. You got the amplifier, takes a little signal, makes it bigger. Filter cleans up all the crap on the signal. Control to tell it, yes, you're on, no, you're not. And a power supply to run it all. Easy breezy. How hard can it be? Right? But that's the thing. If you break it into bite-sized pieces, each of those bite-sized pieces can be broken into pieces. Okay, an exciter will have a modulator. It will have a control circuitry. So again, break it into the little sections as much as you can. Now, different people have different ways of troubleshooting. Okay, a lot of people, I'll do this the other way. A lot of people start at the beginning and go until the signal disappears. Okay, that's where my problem is. A lot of people start at the end and work back until they see the signal. I start in the middle. Got a signal in the middle? Great, go that way. Don't got a signal in the middle? Great, go that way. Okay? However you do it, it all depends on how you think. This comes back to like what we were talking about in the toolboxes. And how many people were in the morning session? Everybody? Nobody? A few missed it. So we were talking about toolboxes, and I said every toolbox is as unique as the engineer carrying it. You know, mine is geared more for stuff that I can get through TSA without having to check bags and generally get probed. So, Ohm's Law. Ohm's law is basically, we're talking volts, ohms, amps, and watts. Watts is what you get, the watts is just how many ohms and amps you got, or how many volts and amps you got. And I like this picture. There are various other ones, some more politically acceptable than others. But that is it in a nutshell. Okay, the volts are the force pushing the current down the pipe. Current is what's running down the pipe, and the resistance is what's trying to slow everything down, for lack of a better word. If you don't take anything else away from today, Google this, print it out, and stick it up on the wall. Because if you're like me and you don't do these, everybody remembers E equals I times R or E equals IV, depending on whether you use electromotive force or voltage, which is the same thing. But no matter how you do it, if you can look at that and break it down in a heartbeat, everything. How many people do indirect power measurements on a transmitter, tube transmitter, where you got the plate voltage, the plate current, and the efficiency? Ohm's law. That's what you're doing. Ohm's law. Everything comes down to that. Now we can throw some filter stuff in there, inductors, capacitors. We'll add Kirchhoff's law and do some nonlinear stuff, and we can make it as confusing as we want to. Trust me, I'm really good at making it confusing. But ultimately, this is the thing that you need to know, because if you know this, you'll be able to walk up to your transmitter, see that the IPA volts are here, the IPA current's here. Well, that's a lot more power than I normally need out of that IPA. What's going on? Okay? Or the power supply volts are high, but the current's low, so the power's the same, but why did the numbers change? Okay, that's the kind of thing we're looking for. And I say a lot of it just comes down to breaking it into those bite-sized pieces to figure out where you're going to look next. Now we're going to talk about some safety stuff in a little bit too, because how many people have never worked on a tube transmitter before? Never ever laid hands on a tube transmitter. How many of y'all have tube transmitters in your group somewhere that you still do need to work on occasion? And see, so for all you that put your hands up first, when the guys that put their hands up second aren't available, you're the ones going to get called. So we'll talk some about the safety, because there's a few things you just don't want to do in a tube transmitter. Now, which I'm going to test y'all. Was it Continental? I think it was the H16, where you have to get to the tuning adjustment, you're reaching in over the power supply. That's depending on the output power of the transmitter, that can be a 15 to 20,000 volt supply that you're sticking your arm over. That's scary stuff. Even if you know what you're doing, that's scary stuff. All right. So this is something else, just a little recap. I just threw this one in here. And like I say, so I'm going to give credit to the Society of Broadcast Engineers, and Gary Morrell is our education chair, by the way. So if you're an SBE member and you do anything to do with SBE education, it probably went across his desk at some point. And he called me up and said, "Hey, you're going to do this." I said, "I don't want to do this." He goes, "I don't care. You're doing it anyway." So this is a very condensed version of an 8-part series that I did with Gary Cavell over the last half of last year and the first part of this year. Um, how many SBE Member Plus members in the room? Couple? Good. Y'all have full access to all of those. I mean, everybody's got access to all of them, but if you're a Member Plus member, you get it all for free. It's part of your membership. Well, if you're a Member Plus member, if you watch 2 of the SBE webinars, you've just paid for the difference to Member Plus for what it's worth. On an 8-part series, you pay Member Plus several times. All right, some more formulas. And I'm not going to regurgitate them. This is the kind of stuff that will let you know. Give you an example. Any AM folks in the room? Tyrone, you can put your hand up. I know you play with AM. Few? So this is the stuff that will let you know if you put a inductance or capacitance meter on a coil or capacitor, you can figure out the resonant frequency in a heartbeat. Okay? Now this is significant because, I mean, a lot of meters, multimeters now have LNC measurement. Well, it doesn't care whether it's a big ass coil or just one of these little board mount inductors. A coil's an inductor's an inductor, right? So if you know what the inductance is and you know what the capacitance is, you can tell what the frequency that circuit's tuned to is. If, as an example, say you've got an ATU, you blew out a capacitor. Can't find that exact capacitor, but I got 2 here that come pretty close. I can stack them together, plug them in. Now I can put my LC meter across the capacitors, across the inductor, figure out what the resonant frequency is, and find out if I'm on my 3rd notch or not, as an example. Okay, this can all be done at low level with the circuit turned off. Now, first safety note. If you're working on an AM and you're out at the antenna site, grab a set of booster cables out of the back of your car or your truck and ground the damn tower. Because on an AM, the antenna is the tower is the antenna, and antennas receive as well as they transmit. And if there's another AM within 20 miles putting out a signal, you're going to have voltage at the base of that tower. Dependent on war story time, and I'll segue off into war stories all the time, forget about it. Some of them are fun, some of them are scary, whatever. I had a guy in Paraguay call me up one day. He goes, "What should I do if I get an RF burn?" And I said, "Well, what you should do is haul your ass to the hospital." What happened? So he was working on one of our 100 kilowatt units. Well, 100 kilowatts is a lot of power, and he recognized that. So he shut the transmitter off, and he dutifully shorted the output of the transmitter with the shorting bar that we provide. Then he walks the quarter wavelength of cable out to the ATU. Gary's already giggling. So for anybody that doesn't know, a quarter wavelength for an RF circuit is the difference between a short and an open, or a little bit of voltage and a whole lot of voltage. And it happened to be that the distance between the short we put at the transmitter and the ATU was just about exactly a quarter wave, about 300 feet. So he gets out there, and what that means is that there's no short as far as the signal's concerned at the base of the tower. He touches the tower. His transmitter's off. The 200 kilowatt half a mile away is not off. And he took 2nd and 3rd degree burns to his hand. And that's a mistake you only make once. He lived through it, so he'll get to make that mistake again, but I guarantee you he won't. I've got friends that have lost appendages doing this. I broke a guy's arm knocking him away from a live 50 kilowatt tower before he could touch it and become part of the infrastructure. Okay, so RF, especially on AM, is frequently present, and it's have respect for it. Understand that it's not trying to kill you, but it really doesn't care if it does or not. So have some respect for it. All right, so a lot of people get worried about solid state transmitters over tube, but when you get down to it, a tube is just a transistor. There's no difference between the two, except that one handles a lot more volts and current than the other one, which is why we stack a whole lot of FETs up to make up what you get out of 13CX15,000. All right, and you've only got 2 real choices. You got current amplifiers and you got voltage amplifiers, but since E equals I times R, into a fixed resistance, I don't care which you're amplifying, the other one's going to get bigger too. Okay? Again, that comes back to that Ohm's law. So we talked, I said earlier, AM and FM. How many people, is there anybody, and I'll ask this, and I know nobody's going to put their hand up because I wouldn't admit to it, but a lot of folks don't. Anybody willing to admit they're not 100% sure of really what's different between AM and FM? No? Everybody knows? Good. Well, we'll go through these ones fast. But so AM, there's two basic options. I mean, you got an audio signal, your message. You got a carrier signal, your FC, whatever, your frequency, 1,000 or 1,400 kilohertz, whatever. You slap them together and you get an amplitude modulated signal. Except if you run an HD or AM stereo. If you run an AM stereo, the L minus R portion of the audio is phase modulated. It's frequency, so it's FM. If you run an HD radio, all the digital carriers are phase modulated. Okay? This becomes important because that means that instead of just designing for the peak voltages, we also have to look at the bandwidth and the frequency response of the antenna system. That comes back to that 2 pi FC math that I had earlier. Okay? So this is the kind of thing, again, not something you're going to need to know day to day, but someday you get caught up or called up on something and it ain't working right. You got an AM that's shutting down with SWR, for example. One of the things it could be is antenna bandwidth, because all of the energy on an AM, well, goes with the modulation. The more high frequencies you got, the more energy at the side bands. That means into a narrow band or poorly tuned antenna, you'll start shutting back with SWR. Okay? Center, it may show 0 reflected on carrier, may be perfect. I'll give you an example. If you're running a low frequency into a Valcom whip, that can be an issue if you don't have matching for it, because the Valcoms are inherently, it's a short whip, 75 feet. They're top loaded, they're naturally resonant at about 5 megahertz. So if you're putting 500 kilohertz into it, or 530, 540, whatever, then you're running into what will be a very high Q narrowband load. Okay, so that's the kind of thing that you pay attention to. Now you can use tuning units to broaden it artificially and dump some power in the tuning unit, and that's fine. But you need to know that that can be an issue. Okay, the other thing you run into a lot is PDM circuitry. You know, whether it's Gates Air uses PDM in their AMs, we use PDM in our AMs, everybody uses some variation of it. I think we may call it PWM in some models and PDM in others. And it's a pretty simple system. Basically, you've got an audio signal, and as you increase the amplitude, you change the duty cycle of the PDM circuit. All it takes is a comparator. You run a sawtooth wave and a comparator and away you go. And it's not real critical to anything except to know that if you lose the PDM circuit, that is the signal that tells you how big your amplifier's got to amplify. So you lose the PDM, you got no output. Okay, so that's a case where a modulator will kill the RF section, just for what it's worth. Okay, so you look at an AM transmitter, remember I said bite-sized pieces, power supply, exciter, amplifier, filter. I don't show the control on this one, but there you go. Okay, pretty easy. And there's not a lot to it. You run your audio signal in, most of ours have a PDM generator in there. What you get out is a varying pulse width. Well, if you filter the PDM frequency out after you've amplified it, because it's a whole lot more efficient to amplify a switch signal than a linear signal. So this is a Class D amplifier. Class D amplifier can be upwards of 95 to 98% DC efficiency. Okay, we don't waste a lot of energy in those. That's the DC efficiency. So that means that I can take that little signal and make it bigger without wasting a lot of power, which means I'm not generating a lot of heat and requiring a lot of air conditioning. All cool. Then I can take the RF signal and amplify it the same way, and then I filter it to get back my sine wave, dump the PDM signal back into a bit high-level audio signal and use it as the power supply. So now I amplify to the limits of the power supply and I got AM. Cool. Overly technical, all I'm saying with it, bite-sized pieces. Break it into the blocks. Okay? And there's a whole bunch of graphics that we're just going to blow through. There we go. So The other thing to remember with this is that various organizations in this country, the FCC, tend to take a dim view on you putting too much audio into the system. On AM, that results in peak voltage. Now, the issue also with peak voltage, and this is something to think about, a circuit designed to pass 5 kilowatts with 125% mod is designed to pass this much peak voltage. If I hit it with 150% mod, I'm above that level, I could cause some arcing. Okay, a lot of times you'll run into a situation, maybe icing or rain getting on the ball gaps where things start to arc. Guy wire insulators are really good for that. So you'll hear things start to arc. Sometimes turning the power down is enough to get it back in control and let you get through your day. Okay, FM signal, same deal. We got audio, we got a carrier, we mash it together. This time we're changing the frequency. Okay, how far we change the frequency is how big the audio signal is. How fast we change it is the frequency of the audio. Except, again, if you're doing HD radio, because the HD carriers are amplitude modulated onto the FM carrier. That gets incredibly important on FM because there's a thing called peak to average power ratio. Basically, again, because the AM carriers are amplitude modulated, we've got to look at the peak-to-peak value of those carriers and add that to the FM. So a signal that's putting out 10 kilowatts, if you throw, and I'll take 10 dB C injection because that's easy math. So 10 dB, 10 decibels is a decimal point, okay? That's the easy way to do it. So like, give you an example, we'll segue off this for a second. So when somebody says 80 dB down, looking at harmonics, that's 0.00000001. I think I got the right number of the carrier. So that's all you got to know about that. The reason I get into that is because how many people have had an LTE interference complaint? Anybody? Couple. I know Matt's dealt with one or two back there, and I know Mark has too, yeah. LTE interference, so the cell companies does anybody here work for a cell company? Good. So the cell companies are typically looking for signals that are about 120 dB down. You remember I said 10 dB is the decimal point. Well, your harmonic limit is already 80 dB down, and they're going 0.01% below that, is how far they're looking. For what it's worth, the noise floor on the FM band is about 95 dB down. So they're looking 25 dB into the grass and trying to find a signal there, which is why anything that radiates out of your FM transmitter, desired or undesired, is going to cause them an issue, almost guaranteed. So like I said, it's not a matter of if you've had an LTE interference complaint anymore, it's when. Everybody's like, 5G will solve that. No, there's a low band version of 5G that happens to fall right on 700 megahertz. Now, relative to 100 megahertz FM carrier, where's 700 megahertz? Oh, it's the seventh harmonic. Lovely. All right. So again, back to the FM carrier, bite-sized pieces. Okay. So we got the exciter section, amplifier section. We got a filter section in here. This is just the exciter portion. But then there's the amplifier. So it's all the same stuff. Again, every transmitter in the world, same 5 blocks. Okay, now what's inside those blocks, that's going to vary. Okay, whether it's a Class C amplifier, a Class D amplifier, whether it's a Class A amplifier. That'll be designed or determined by the circuit design. But how you troubleshoot it, same deal. Whether you start at the beginning, start in the middle, or start at the end, totally up to you and how you like to do it. I'm not going to read that. I just said it 5 minutes ago. Okay, but that's the kind of thing that we need to know. When you're looking at a signal, when you're troubleshooting a signal, pay attention to what you're working with, because that will tell you what you need to think about. And remember, the E equals I times R. If the volts and the current, one or the other, doesn't make sense, something had to change, and it can only be one of those 3 things: the volts, the current, or the resistance. Something shorted, something opened. Typically, if it opens, there'll be visible signs. Usually, if it shorts, it'll open shortly after if you hit it hard enough. there's something else. Best way to troubleshoot an intermittent problem is to make it a permanent problem. You laugh, but if you've got an intermittent problem and you blow it up real good so the smoke comes out, now you know where to look. Okay, here's something else to think about, and this comes back more to the tube rigs than the solid state rigs. When you're looking at AM noise, and the one that is the biggest issue, especially on tube rigs, is typically power supply noise, asynchronous AM noise. That has an immediate and direct impact on coverage. So if the GM comes to you someday and says, we're not going out as far, I can't hear it in my living room like I used to, and you look at the transmitter and it's still making 50 kilowatts or 20 kilowatts or 10 kilo or whatever it's supposed to normally make, measure the AM noise. Okay? That may be that you may have power supply ripple causing you a problem in an exciter. Okay? Meanwhile, power supply in an exciter can directly impact your coverage. Just as an example. All right? So that's, again, one of those little troubleshooting techniques that you don't really think about because we're making power. How can we have a problem? AM noise can be your problem in a heartbeat. Other thing to remember, when we get into higher frequencies like FM or 900 meg STLs, a piece of wire can be an inductor, a capacitor, or both, depending on how you route it and where and how long it is. All right, and this is significant. This is why we use coax, because of the balance, the feed and the return. And I was talking to somebody earlier, they were mentioning that they had a big honking 6-inch 75 ohm coax. And I said, as long as your source impedance and your load impedance are both exactly 50J0, the impedance of the line is irrelevant. But if you get any mismatch at either end, get a little bit of antenna icing, get some detuning on the transmitter, either one of those, that impedance mismatch on the line will magnify the issue that you see, or the result. Where it becomes a challenge is if you burn out that line because the mismatch got bigger than you expected it to. Matt, I hope you're going to, if I start lying on anything, I expect you to wave your hand or something and say, dude, that's not right.
Doing a great job.
Awesome. So I mentioned early on my screen background on my laptop is the baseband. And this is a wonderful thing to have. I mean, this is taken directly, this is off our user interface, the spectrum, spectrum analyzer on our FM rigs. You can set it to look at the carrier or to look at the baseband. I want to look at that because in a heartbeat, I can tell you the health of my system. I've got my carrier's way down there at 0, I can't see it, but I've got my L+R audio, I've got my stereo pilot, my L-R, the pilot suppression tone, my RDS, all right there. If you look at it enough, you get a fix for where the levels of the pilot versus the RDS should be. Okay, so for what it's worth, this is a 9% injection pilot and a 5% injection RDS. Okay, so at a glance, you can take a look at that and you can say, okay, cool, everything's good, everything's there. Now, if I'm driving down the road and I see that my RDS carriers are there, I know they're there, driving down the road and I don't see the RDS display on my screen, that means the data's not making it to the modulator. Now, where are you losing it? Could be the automation system, could be the STL, could be the transmitter. This is where the IT geeks get to have their fun. Little program called Port Peaker. Okay, you can Google. Anybody got it? Anybody played with it? Port Peaker is awesome because you can plug it in at the transmitter site, into the network at the transmitter site, scan the IP address and port, which is 7005 for our transmitters, for the RDS signal, and you should be able to read the RDS data in the ASCII text coming through on the port scan. If you can see that, you know the data's getting to the transmitter, and now the problem's in the exciter. If you can't see that, you got a network path problem and you're not getting the signal there. Again, bite-sized pieces, start and middle. Okay? Now, NRSC has set a lot of the specifications related to RDS and stereo. So the recommendation, 9% for the stereo pilot, you do get some improvements in coverage by going mono. Not so much anymore with the cars that are out there these days. Home listening may be different. Anybody got a diversity receiver in a car? Those are the coolest things ever, man. Those things will pick a signal up where you can't get it on any other receiver. Anyway, RBDS, NRSC recommends 5%. I'm running my station at 4 because we are at a massive altitude in an area where there's not a lot of steel frame buildings. It's all wood frame construction, and most of our audience is mobile. And at 4%, my RDS will drop out about the time my signal gets scratchy. So we drive tested it and turned it down a percent because I didn't want the RDS outrunning the signal. Okay, and that'll be kind of up to you. All right, now I'm not really doing an RDS discussion, but if you have a system, like a lot of the newer transmitters, you can take the automation system, feed it directly into the transmitter as ASCII text, and it'll kick it out. Some of them need you to mangle the code a little bit. Guy in the audience right there has developed this really cool little toy called RDS Express. So Mark, you want to stand up and wave your hand? There you go. So if anybody, so Mark's the inventor of RDS Express for what it's worth, and it's a pretty cool tool for helping out with sometimes you get some challenge with that. You can buy outboard, sidechain, or inline RDS generators like Innovonics. Is Automat still doing one? Anybody know? I think they did for a while. Then Pierce CZ, there's another good example. Yeah, there's a bunch of them out there. All right, acronym time, not going to read them all. I think I've mentioned every single one of them at least once except for SCAs. By the way, RDS is an SCA for what it's worth, a subcarrier. That is a good point. If you are in one of our boxes using an external RDS generator like an Innovonics, or the Automat was the 50 something, I don't remember. But if you're using an external one, you've got to turn the RDS off in the transmitter and turn the SCAs on, because it's looking for that 57 kilohertz SCA coming in on the composite signal. So that, again, troubleshooting tip that may or may not come in handy someday. You what? Yes. Well, always back to the original NV when we started doing internal RDS generation. We'll have to fix that someday. All right. I'm not going to beat my drum on this. We combine transmitters a lot of different reasons. Some people do it for main standby. And we had this conversation outside earlier talking about how you can add all manners of redundancy, but when you run them all into a single combiner and a single antenna, you haven't got redundancy. You've just got multiple systems with one point of failure at the tail end. So if you wanted true redundancy, you'd have 2 transmitters, 2 antennas, ideally in 2 separate locations, so when the tower falls down at one, you still got a signal on the air. Okay, so that's something you talk to your manufacturer of choice and figure out a solution that works for you. I mentioned earlier with FM that the digital carriers are amplitude modulated. They also go on the outskirts of the AM or the analog. And this is only important because how many people are running HD radio? Bunch. If you tend to overmodulate a little bit, like running 110 to 120%, and I'm not saying anybody does or doesn't, but I do have a screenshot from a translator that I may or may not have hacked into yesterday. And 125% was where their mod monitor was locked. With almost no, what do you call the dynamic range? Yeah, no, it was welded at 125%. Anyway, if you do something like that on an HD signal, you will start stepping on your digital carriers and things get a little ugly. By the same token, if you start to ice up the antenna and the tuning goes off, you can have some issues. So it's just something else to pay attention to, okay? E equals I times R and bandwidth. Okay, so peak voltages are important on FM especially when you're running HD. And I wanted to mention that just because I've actually seen somebody flame out the line because they went through, oh yeah, no, the antenna's sized perfectly for this peak power. The line and the transmitter, and this is all wonderful. The line was not rated for the peak voltage they were hitting it with a 10 dB signal, again, 10%. So same analog TPO, but add 10% that much power again for digital, and then multiply that by 4 to get the peak to average ratio. They were running about 20% more than the line would handle, and it handled it until the first time the antenna iced up a little bit and threw that mismatch in there and screwed the whole works up. Okay, so that's something to pay attention to. Nothing there really critical. We're coming close on time, so we'll just skip through. This though, this right here. Okay, so I mentioned that take the Ohm's Law wheel is the only thing you take away. No, take this too. Cool, clean, well grounded. Okay, if you do those three things, any box will last a whole lot longer. Now, I'm not guaranteeing that shit ain't going to go sideways, that the power company, forgot we were recording, whoops. The power company throws some really nasty stuff down the line, okay? We can't protect against everything. But keeping it cool, forcing enough air through it, and by cool, I don't mean cooling the room, I mean cooling the equipment. Okay, I don't care if the room's 110 degrees as long as the transmitter's at 70. Something to think about. Fans, electrolytic capacitors, to name two, every 10 degrees Celsius or 18 degrees Fahrenheit that you drop the ambient temperature, you double the lifespan. That's not insignificant. Now, I'll give you an example. So the fans we use in our GV series, the little itty-bitty 2.5-inch muffin fans, you got a whole bunch of them. It sounds like a hive of angry bees. Those things are rated for a nominal 5-year lifespan at 40 degrees Celsius or 104 degrees Fahrenheit. And I'm bilingual, by the way. I speak English and American. So for every 10 degrees Celsius or 18 Fahrenheit, you double that lifespan. So at 30 Celsius or 96 Fahrenheit, 98 Fahrenheit, 96, I was right the first time, then you're at a 10-year lifespan. At 20 Celsius or 68 Fahrenheit, now you're at a 20-year lifespan. This is nominal. I mean, back pressure will decrease it. Running lots of air through it and decreasing back pressure will increase it. But that's the basic rule of thumb. Now, you hit a point of diminishing returns. You know, you're not going to take the site all the way down to absolute zero, but if you could, you'd have infinite lifespan. Yay. Except it all frees solid because things with lubrication in them don't tend to function so well when the lubrication gets thick. So balancing out, but that's the kind of thing to pay attention to. So we want to keep it cool, keep the air going through it. This is the one that I see the most. People blowing the air past the stuff at 1,000,000 miles an hour. Don't blow the air past the transmitter, blow the air through the transmitter. Okay, I run into that a lot. It creates a negative pressure zone behind the transmitter. In a lot of cases, you'll end up pulling air away from the box instead of pushing it through. Don't do that. Okay, by the same token, if you got one of those one of those not to be named mini splits or split level air conditioners where they shoot the cool out the top, cool air goes out the top, settles down. Wonderful for an office building or a space like this. Nobody gets a draft in their face. The cool air goes out and settles down. Life is good. 180 degrees out of phase for doing a broadcast transmitter because transmitters run the cool air in down low or in the back somewhere or in the front, depending on the transmitter. Hot air gets shoved out the top. Well, if you got this kind of system, you're just mixing your cool air and your hot air and doing absolutely nothing to anything. And then down here, you're pulling the cool air away from the transmitter. So again, starving the transmitter for airflow. Okay, so don't do that. If you got to, invest $1,500 in sheet metal tech. Your HVAC guy will have one. Yeah, I know, zero time. That's why I shut it off 3 minutes early, see? But have a sheet metal guy, reverse your goes into and goes out it. So you're dumping the cool air out or to the transmitter air intakes and pulling the warm air back from ceiling level. Okay, that will save you a ton. Especially some transmitters have a little more internal back pressure or a lot more power density and kick out much hotter air than others. And if you do this, you will extend the life of that transmitter dramatically. Okay, and I don't care whose logo's on the front of it. Us, Gates Air, BE, Rhodey. Well, not Rhodey, they're liquid cooled. However, good point. On a liquid cooled transmitter, you do need to go outside and clean those heat exchangers every now and again, especially in that period of year called cottonwood season. Like it almost, for Gary's neck of the woods, that's almost a weekly occurrence for the month of June and July. Okay, if you're running forced air, check the air filters on occasion. I didn't put your picture of your site up on this one. So I did a tour through Minnesota, Wisconsin, and Michigan one June, and I stopped at a bunch of sites, and I took a picture from each state showing an air filter totally clogged solid with cottonwood fiber. One of them happened to be one of his. And he just cleaned it like a couple of weeks earlier. It's like I tell people, the maintenance schedule that you use will be totally decided by the condition of the site and the environment. It's nothing I can tell you. I'll tell you how often to tighten the hardware. Okay, grounding, short straight runs, don't do them like this. You don't need ground loops, and do not run your ground wire through a steel conduit if you can avoid it. Now, if you're in a high rise and they have to have the ground wire enclosed, use PVC, because we don't want to create a ferrite. We don't want to add resistance to the path we want our lightning to take. Okay? So a few more things, we'll just leave them up there for the recording, skip through that. Going to hit PPE for a very quick second, and we are pretty much out of time, so we're going to go fast. But ESR rated footwear will save your ass if you do something stupid. I've done something stupid many times. Apparently I'm really good at it. It's one of the few things I'm really good at. And I love my ESR footwear. You can buy this stuff at Walmart. Now down here in Canada we call it ESR, electroshock resistant. In the US it's called EH rated, electrohazard. And you buy them at Walmart for $100 for a pair of carbon fiber toed sneakers with the shock. All the shock resistance means is you put 18,000 volts across the sole, it won't pass more than a milliamp of current. And if you get into that 317 power supply to do that adjustment and come up against that, and you're wearing shock resistant footwear and don't have your knees on the floor, it can be the difference between a really bad day and a not so bad day. If you work in AM, you better be familiar with that. Ground wand, or what everybody else calls it. I won't even bring it up in here. If you don't have one, wooden broomstick, a roll of duct tape, and a jumper cable. Bang, ground wand. Please make sure it's a wooden broomstick. Because I'm here to tell you, hitting the high voltage supply while you're holding a metal broomstick would just be a bad idea. Don't do that. Okay, I mentioned thermal scan earlier. Love those things. I use the FLIR because they're $257 delivered to my house. But whatever you choose, scan your temperature stuff. All right. Online information. If anybody has a question, you just one or two real quick, but then we'll go. If there aren't any, we'll just call it a day and let you on your way. Tick, 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 tick. Thank you very much. Only 2 minutes late.
I don't think anybody's counting.
Sure.
Very cool, yeah. All right, thanks for a great presentation from Jeff here. We will now take a short break sponsored by Q, and we'll reconvene at 3:25 for our closing general session in rooms D281, 282, which I believe is a couple down the hall. Just a reminder, our afternoon door prizes, including the Sony 4K television, will be given away at the beginning of the closing session, and you must be present to win. All right, thanks everybody.